That's the biggest department in the faculty, where there are 12 research groups going from analytical chemistry to organic chemistry. And for instance, so the group that I'm leading is called the Particle and Interfacial Technology Group. I will have some introduction in the next slide. So within that one, actually, the research that I'm doing and the PhD students in our group are doing is about colloid science in general, small particles, actually linked to emulsions and dispersions. There are two other professors, Meeren and Cornelissen, whose research is related to water technology, where they do a lot of research on membrane processes like electrodialysis, ultrafiltration, reverse osmosis. That's actually the composition of this part. Particle interfacial technology. So the things that we are studying is actually, well, we are quite equipped. We have quite a number of techniques to measure particle size, going from some nanometers to some, well, up to about 1 millimeter with several techniques. Surface charge is also an important property, both for particles and macroscopic surfaces here. And for instance, for emulsion research, actually also interfacial tension, dynamic interfacial tension, interfacial rheology is actually also an important technique to know something about what happens with an emulsifier at an interface. And rheology is another aspect for concentrated dispersions. And the research we are doing is well, it's rather fundamental, because there is also a food technology department which is more applied. But anyway, the topics are mostly related, or they can be related to different fields. What I will present today is mainly linked with food technology, so that's about all the research on emulsion preparation and stability. As was said already, originally mainly focusing on oil and water emulsions, then switching to water and oil, and in the last decade quite some research on double emulsions. But in the past we have also done some research, for instance, quite some research on the bersama encapsulation. It was actually already part of my PhD work quite some time ago, which was, for instance, together with Procter & Gamble, because producing, for instance, fabric softeners, which are actually also concentrated liposomal dispersions, and where the perfume components have to be incorporated there. So there are different fields. And in the past we also did some work on suspo emulsion formulations, nanosuspension formulations. That was together with Selasa Pharmaceutica, a big pharmaceutical company in Belgium. It's basically always about particles, mostly small particles, being present. If you want to have some more information, then you can find the website here, where you can find some, for instance, also link to publications. Alright. Let's come to the topic of today, about emulsions. And well, let's, as we all know, actually, if you consider water and oil and you put them together, then actually they do not like to mix. They are typically immiscible. Here, on the other hand, you can make kind of a quite homogeneous mixture, but there is like two requirements. The first one is actually to add an emulsifier to help this process, and in addition, quite some energy input is needed to break up the one phase into the other one, and then actually, well, mostly determined by the type of emulsifier that is used. Then you can either end up with having oil droplets dispersed in water, so indicated as an OW emulsion, or you can have the other case being water droplets being broken up and being dispersed in an oil phase. That's actually then a simple emulsion. And actually a typical example of an emulsion is mayonnaise, which especially in Belgium is very popular to eat together with the French fries. Actually what you have there is a concentrated emulsion of oil in an aqueous phase, which consists, for instance, of vinegar. But if you want to make mayonnaise, you need to have energy input, and typically you also use an egg yolk, and that's actually your emulsifier here that then enables to have your oil dispersed in the aqueous phase. Here you see some other examples, typical examples, food examples of emulsions. Talked already about mayonnaise as a typical oil and water emulsion with a very concentrated oil and water emulsion. Milk is then a more dilute oil and water emulsion. Some kind of dressings are typical examples. And if we talk about having water droplets dispersed in oil, that's actually typically the situation in butter. There is about 16% of water in the form of smoke droplets dispersed in the fat phase, or also other kinds of spreads are actually water and oil emulsions, where actually nowadays more and more in low-calorie fats spreads, there the water content will be equal to 60% of water droplets in a continuous phase of oil. Now, of course, what you see if you have looked, for instance, for this kind of oil and water emulsions, so like dressings or mayonnaise or whipped cream, if you want to have some kind of structured product, then typically we have a quite high fat content. If you have a low fat content, like in milk, then actually the structuring effect is quite limited, so you have a very liquid-like product. And of course, that means that if we need actually a high amount of droplets here for your functionality, for your structure, well, fat is actually quite energy rich, so that leads to the fact that these kind of products have a high caloric content, and that's then of course a little bit of a problem, because actually what we have is that surely in Europe, even more in the United States, there's more and more problems with obesity and overweight. Actually, here there are data from already more than 10 years ago, where actually the problem is already quite clear, having over 50% of people with overweight or being obese, and actually over 20% being obese. It will surely not have decreased in the past 10 years in that case. And that's of course linked with the energy intake. So that means that actually products with a high calorie content should be avoided, or we should try to find solutions to reduce the calorie content of foods. And then actually we come to the topic of double emulsions, having water in oil and water technology, because we said already that to have your functionality in the product, that there should be a sufficient volume fraction of dispersed phase. But what we can do, or what we do in double emulsion technology, is that actually instead of having your dispersed phase being made up completely of oil, well, if we can replace it partly, or if we can fill up the oil droplets with water droplets, then of course it means that we will have much less oil in the same product. So if we need to have, for instance, 50% of dispersed phase, but if, for instance, half of that oil droplets can be filled with water, then in practice you have only 25% of oil to have the same kind of structuring effect, to have the same amount of dispersed phase. So here we talk then about a double emulsion, because there are like two emulsions. So the first type is your water in oil emulsion, and that's then actually emulsified in a second phase. A double emulsion in general, we can talk about multiple emulsions here, so if there is more than one dispersed phase. And in this case, we have the water dispersed in oil, which is then again dispersed in water. So that's actually what is indicated. Okay, so that's actually, well, the research we're doing is mainly linked with this kind of water in oil and water emulsions. That's actually also in scientific literature what is by far most widely studied. From time to time we also counter the opposite. For instance, in fat-based systems like spreads, for instance, oil and water in oil emulsions can be used. And talking about multiple emulsions, basically you could also have, you could even go further to have, for instance, again, oil droplets dispersed into the internal water droplets. That is what we have here. Here to the right you see kind of a general scheme, so then we also talk about, to indicate the two water phases. It's frequently indicated as W1 phase, indicating the internal water, and the W2 being the external water. And of course in this case, again, emulsifiers will be important. We need to have an emulsifier to stabilize the water droplets in oil, which is typically an oil-soluble emulsifier. And you need to have a second emulsifier to stabilize that oil-water interface here, which is typically a water-soluble emulsifier. Alright, Now that we know what double emulsions are, so let's then have a look for what we did during the last decade, starting with some aspects on preparation. And if you're talking about preparation, then mostly, and also what we do in our lab, we always use a kind of a two-step emulsification process. We have two emulsions, so what we do in that procedure is that you start by having water, which can contain some kind of water-soluble ingredients. That's especially if you want to do some encapsulation, for instance, of water-soluble ingredients inside of your oil droplets. Then actually your encapsulated ingredients, water-soluble ingredients, are added in this first water phase. And so in the first step, that water phase is dispersed or is emulsified into another phase. And as we have seen in the beginning, actually that depends on your emulsifier. Typically here, a lipophilic and oil-soluble emulsifier is used. The one that is mostly used in is actually polyglycerol polyricinoleate, is a kind of a synthetic emulsifier. Is actually a very powerful emulsifier for this application. But that's syntactic, so part of the research that we have done was also to try to replace that PGPR by a more natural surfactant such as lecithin, soybean lecithin, and especially then PC depleted lecithin can be used also in some cases. In that first step, so we make a water in oil emulsion here, and actually then this oil phase is then actually used in your second step. So that oil phase is then actually emulsified in your second water phase in the second step here, and such then actually you end up with that oil phase, so you oil with your internal droplets here being dispersed in your external water phase. And as we said already, in that case, then you use a hydrophilic emulsifier, which can, for instance, typically be for food applications, can be also just a protein, like whey protein isolate, or sodium caseinate, or it can be some kind of typical water-soluble emulsifier. Here you see, for instance, what we quite frequently do, or the typical scheme that we use, is actually to have about 50-50 mixtures in the two steps. So it means that you start with equal volumes of the first water phase and the oil phase here. That actually gives rise to the primary emulsion, and that's then again mixed in equal volumes with the external water phase, so that finally you end up with a double emulsion that contains 50%, and theoretically contains half of the volume being external water, half of the volume being your dispersed phase, and actually in your droplets then it's actually half water and half oil, so there's actually 25% of oil, 25% of internal water, and 50% of external water in that kind of situation. And you see indeed here the typical emulsifier that are used are that polyglycerol polyricinoleate on the one hand, and a protein like sodium caseinate on the other hand. Okay, that was well, that's at least what we expect if we use that kind of emulsifier, that the internal water is remaining inside of the oil droplets, that the other water phase is externally. But how can we know whether this really worked? So how can we characterize what we made? And actually there is a number of aspects that are important. We can show the whole thing together. Some of the terms that will come back in the next slides is, for instance, the first one is actually referred to as the yield. The yield is actually linked with that water, the amount of water that we had in the first step. So we said that we had the first water phase that we wanted to disperse into the oil phase. The yield that actually indicates to what extent that original water that should be present inside your oil droplets, to what extent it is really still present in your oil droplets. Because when you're doing quite some processing, there is a chance that actually your emulsion droplet get disrupted. So it could well be that part of that water is actually escaping from inside of the oil phase to outside. So that's actually your yield, the percentage of water that remains internally in your oil droplets after the second step. And for that one, we use mainly two techniques that I will explain in the next slides. If we're talking about encapsulation of something in the first water phase, then the encapsulation efficiency is another important aspect, which is then saying from that water-soluble component, to what extent does that remain really inside of the oil droplets, or can it also gradually escape and be released, which normally we do not like, so that's actually encapsulation efficiency. And droplet size will be also important. Droplet size, where of course we can have a look for the internal water droplets. That's actually the more challenging job. Actually, for that one, there can be low resolution NMR can be used. So-called gradient NMR diffusometry can be used to measure the size of your water droplets inside the oil phase. To measure the size of the oil globules, that's actually much simpler. That can be just done by simple laser diffraction, which is the more, let's say, the kind of standard technique for particle size applications. But I said already there, actually also here, dilution is important. We will see some examples later on. So you should make sure that the osmotic strength of your dilution liquid is the same as your original emulsion, because otherwise also you will not have good measurements. Starting with characterization, of course, the most direct characterization is just to have a look through a microscope. And here you see some pictures. The one to the left was obtained by confocal laser scanning microscopy, where actually the oil phase was stained with Nile red. So the oil is indicated in white, whereas actually Nile red is not water soluble, so the water phase is shown in black. So you see the external water, you see your oil droplets, where you see indeed that within the oil there is again black droplets there, so that there are water droplets present indeed within your oil droplets, and actually there are a lot of them. Actually also already with simple light microscopy you can see the same things. So here you see your double emulsion droplets, and you see that actually they are fully packed with small internal droplets in this case. What you also see already here is that typically these double emulsion droplets are quite big. So here you see a scale of 50 micrometers. So they are typically several micrometers to even several tens of micrometers. They are typically an order of magnitude bigger than your original water droplets. And if the original water droplets are of the order of 1 micrometer, then actually you come to about 10 micrometers for your double emulsion. Okay, we see that there is water. The question is how much of water is then still present? And I said already that basically there we can use two techniques. The first one being analytical photocentrifugation. What we do in this case is actually apply a centrifugal force to the emulsion, and that of course makes that all droplets will have a tendency to cream. So by forcing creaming, then basically what we'll have is, if we consider the volume of the cream phase, that of course contains the oil, but the cream here also contains the internal water droplets. So actually by measuring that volume, we have an idea of the oil and the internal water. From the composition of the emulsion, we know how much of oil was added. So actually as such, we can then actually calculate how much of water is still present internally. And of course your serum, that's actually your external water phase. How to do that one? Well, to quantify this one, that actually can be done by photocentrifugation. Is actually a technique where you use light going through your sample during centrifugation, and as such you can actually have a look where the green phase is and where the serum phase is present. And so then we can just calculate the yield. So I said already, if we subtract the volume of oil here from the volume of the cream, then actually we just have the volume of the internal water that is still present. And if we compare this to what we have added in our formulation, then actually we know the yield. Just to give you an example, here you see a result of such a kind of analytical photocentrifugation. That's an instrument that is called a Lumifuge or a Lumisizer. That's actually a German company, Lum. What you do in this case is that they have a look for the transmission through your emulsion sample during centrifugation, and actually here you see the profile at the end of the centrifugation process. The x-axis indicates the position relative to the center of rotation, so it means that this is the bottom of your emulsion here, and so this was originally the top, so that's closest to the center of rotation. And what you see after centrifugation is that there is a layer here with a high transmission, so that's your transparent serum phase, and there is a layer with a very low transmission, so that's actually your cream phase. And what was shown in this case is actually emulsions with 25% of oil. Actually what you have in blue is also containing 25% of oil, but you see in this case already that indeed the cream phase is actually much thicker, that it takes about half of the total volume. So actually the additional volume that is taken here is because of the internal water that you have. So there is about 25% due to the oil, and the additional part is due to the enclosed water. So as such, we can actually determine here the thickness of your cream phase, so the volume or the percentage taken by the cream, which is needed for our calculation. That's one approach here that surely can be applied for emulsions which are quite low in viscosity, so that there can be some easy creaming. In the case that we have quite structured emulsions, then centrifugation might be not sufficient to have a complete separation. And actually in that case, we can also use a kind of another low resolution NMR technique, which is called T2 relaximetry. What you do in T2 relaximetry is you can measure the so-called T2 relaxation time. And if you do this just of water, so if you put in a sample, just water as your sample, then water is characterized by a T2 relaxation time of about 1 to 2 seconds. So this is what you find here. If you add some ingredients like manganese chloride, it's called a paramagnetic ion, the manganese ion. The properties of this one is that if these ions are present in water, that your T2 relaxation time is strongly reduced. And so, for instance, here you see that if you add a little bit of manganese chloride to water, that then your relaxation time is shifted from about 1 second to something like 50 milliseconds. So there is quite some effect. How can we use this now for double emulsions? Well, if we do a T2 relaxation analysis on a double emulsion, then what we'll find is basically peaks in two regions. You see on the one hand a big peak due to your water, and actually in your double emulsion it doesn't really matter whether the water is present outside or inside the droplets. That's basically the same kind of properties, so that's still that kind of relaxation time of about 1 second. And there is another contribution, that's actually your oil phase here. Oil has typically a very low relaxation time. Actually the relaxation time is somewhat inversely proportional with the viscosity. Okay, here we still cannot see a difference between internal and external water, but if we now have our double emulsion and we add a little bit of manganese chloride, then actually the manganese chloride will be mixed with the external water phase. But manganese chloride, it's actually the manganese ions which are important. The manganese ions, they are not soluble, they are soluble in water, but they are not soluble in the oil phase. So the manganese ions, they cannot enter the oil phase, and if they cannot enter the oil phase, then they can also not enter the water phase that is present within the droplets. And so you see, if you now do your analysis of your T2 relaxation, that indeed the peak for water has been split. Part of the water has still a relaxation time somewhere in the neighborhood of the 1 second. That's actually the water that is present inside, because that one was not affected, or only weakly affected by the added manganese here. Whereas the external water, that was actually strongly affected by your added manganese. So you see that now we can make a discrimination. So if you determine the peak area, that's proportional to the amount of external water, that's proportional to the amount of internal water, and we still see here the oil phase composition. So now actually we can calculate indeed the entrapped volume, which is the ratio of the inner water to the total water. That's actually just the ratio of this peak area to the sum of these two. So your internal water is here and your total water is there. So there are indeed some techniques to know something and so to characterize your emulsions. Just to give you an idea, that's a kind of an illustration of that kind of principle. What we did here was actually also make double emulsions. In this case, it was actually finally a kind of a 20-20-60 composition here. So it means that in this case, the closed volume, theoretically, you expect 25%, 20% of internal water, and the total amount of water is the 20 and the 60, so that's 80, so 25%. What was done in this case was that actually the enclosed water fraction, as determined by NMR, was actually measured as a function of the mixing duration during your second emulsification step. And what you see is that as you continue here mixing during that second step, is that actually your enclosed volume is gradually reduced. So actually there is some kind of damage of your droplets by continuing the shear effect for a longer time. More and more actually the internal water is released to the external water phase, so you break down droplets. So in this case, you see there is a kind of a balance, because increased mixing, that's actually good. You also see that actually your multiple emulsion droplet diameter is shown. For droplet size, actually it's preferable to have smaller droplets because they cream less rapidly. So here you see that you have to make a kind of a compromise, because actually the desired effect is to reduce droplet size, but as you make droplets smaller, you also lose part of your internal water. So that means that it's sometimes you have to make some compromises. And of course, if you lose internal water, then it means that you also lose that beneficial effect of having calorie reduction in that way. Alright, let me look. Recently, we, in a current PhD, we have extended that research. There is here maybe quite a lot of data. What we did in our more recent research was actually to have a look for variations in the mixing intensity, both in the first emulsification step and in the second emulsification step, where actually we vary the mixing intensity by, on the one hand, using a kind of a shear application. Ultraturix is a rotor stator mixer, which we applied at 3 different speeds, so actually increasing the intensity of emulsification. And actually, if you use a microfluidizer that's comparable to a high pressure homogenizer, then actually you can even have a more intense homogenization. And that microfluidizer is driven by air, but the liquid pressure is then typically 140 times bigger. So if you use 6 bar of driving air pressure, then actually you're doing an emulsification at about 800 bars of liquid pressure. So that's even more intense. And for instance, what you see that here is the results of the particle size of your double emulsion droplets as a function of, on the one hand, the mixing intensity of the first step, Ultraturix at 6,500 RPM, 17,500, 24,000, or microfluidization. And within every group, actually you also see that the same kind of intensity was also used in the second step here. What you see in this case is that it's especially the second step that determines your final particle size here, so that's very decisive. Whereas actually if you have a look for the effect of the primary emulsion step, so making water droplets in oil, then actually your first emulsification step has actually only a weak effect. You only see if you compare the different groups, you only see actually a small effect. So the second step is actually the most decisive one for particle size. Here we have to look for entrapped water yield, how much of the water that should be present in your oil droplets is really remaining there after your intense emulsification conditions. And what you see there is that if you use Ultraturix processing here, then actually your yield of internal water is about 100%. That's quite okay. But if you use microfluidization, you see already that if you use microfluidization in the first processing step, that the yield is already only 50%. And even if you use Ultraturix in the first step, but you use microfluidization in the second step, also then actually you lose the water. So that's the effect that we have seen a moment ago. If there is too strong of processing in the second step, you're breaking down your droplets too much, and that means that also the internal water droplets become disrupted and the water is released to the external phase. So here you surely see again that microfluidization is the more powerful technique, but that actually for double emulsions it's like too powerful. Ultraturix is actually by far the preferential or the best way to make your double emulsions. And we also had to look for encapsulation efficiency. In this case, we used a kind of one type of amino acid, valine, as a kind of a typical component, because that one can be easily analyzed, for instance, colorimetrically. Again, actually, we see kind of a similar effect, is that your encapsulation efficiency was quite high, typically 90 to 100%, by just using ultra-Tureks, especially in the first step, but also in the second step. But again, actually with microfluidization, here in your second processing step, having a detrimental effect in this case. So this shows you here that actually the processing that is applied is actually quite important for the overall properties of your double emulsion. That's, I guess, a little bit, we'll skip that one because otherwise we will run out of time. We did some other work on formulation, so about the composition that we had. And one of the aspects is, an important aspect there in double emulsions, is the concept of Oswald ripening, which also occurs in water and oil emulsions, and hence also in double emulsions. What about Oswald ripening? Oswald ripening is actually the effect that if you have different size of water droplets, that actually the solubility of a material in the continuous phase is bigger for smaller droplets than for bigger droplets. So if your solubility here is bigger, then it means that here molecules go into solution in your oil phase around it, and as material here goes in solution, it can diffuse towards your bigger droplets, and there then become precipitated because of the fact that there your solubility is lower. And then of course if this happens, then it means that these smaller droplets become smaller, the bigger droplets become bigger, and that finally will lead to the fact that the smaller droplets will completely disappear, and that the bigger droplets have been grown. So that's a typical thing. It's not occurring in oil and water emulsions, because the solubility of oil in water is too limited. But for the other case, actually water in oil, well actually, water is actually quite soluble. You can have quite some water dissolved even in triglyceride oil, and then actually it typically can happen. How to prevent that one? Well, actually we can use so-called Oswald ripening inhibitors. And Oswald ripening inhibitors, they are typically hydrophilic solids. It can be a salt or a sugar dissolved in the water phase, that actually here indicated by the yellow dots. Because what happens in that case, if you have a salt or a sugar, well, that actually will not, the solubility in water is there much lower, solubility in the oil phase of your hydrophilic solid is much lower, so it can hardly be dissolved and hardly be transported to the other phase. And so that now means that if water starts to migrate, then you see that actually as this droplet shrinks, that actually its concentration in your hydrophilic solute increases. And if water goes in here, then actually this becomes expanded, so here your concentration becomes lower. And as such, now it means that automatically you will have then an osmotic gradient, because if you have here a higher concentration of your solute and there a lower concentration, then the osmotic strength there will be bigger, and so your water will be sucked back by osmotic effects. So as such, actually you prevent that your small droplets are going, as water is transported there, you have a shrinkage. If there is a shrinkage, you have the osmotic effect, which actually makes that now you return to the original situation, and that you do not lose your small droplets. That's at least what you expect theoretically, so that actually by having a water-soluble component present in the water phase, that you prevent Oswald ripening. And that's indeed what we can also measure experimentally. So what you see here is actually the size here of the water droplets in a water and oil emulsion during storage here for about 1 week and a half. And what you see in this case is, on the one hand, we have that water and oil emulsion with just pure water, nothing added to your water phase. And then indeed you see that actually your particle size is gradually increasing over time. Actually you can show theoretically that if you have Oswald ripening, that actually the water droplet raised to the third power should increase linearly with time. and that's indeed what you see here, is that the size raised to the third power indeed increases as a function of time due to that Oswald ripening effect. What you see here is that if you have a similar emulsion, but with glucose dissolved in the aqueous phase, then indeed your size actually does not change during the same storage period. So glucose, just as any other kind of hydrophilic solute, actually is very effective in preventing this Oswald ripening. So you see the Oswald ripening inhibition effect of a water-soluble solute. So that's already something important to include in this one. So in water and oil emulsions or double emulsions, actually you should always have a water-soluble component present to prevent that Oswald ripening effect. I said already that we also did some work on trying to replace a synthetic emulsifier like PGPR with a more natural emulsifier like lecithin, because lecithin is typically obtained as a byproduct of oil purification. Typically it can come from soy or from corn lecithin, so that's a natural emulsifier. And what was done in this research was actually to have a look for the composition of your oil phase. If you use high oleic sunflower oil, so kind of a normal triglyceride, so-called long-chain triglyceride, that was actually compared to so-called medium-chain triglyceride, which mainly contains, I guess, C10 and C12 fatty acids. So actually in this case, so comparable emulsions were made, so the only difference was actually in the oil phase, being high oleic sunflower oil or MCT oil. For the rest, you see that in this case again, glucose was added so to prevent an Oswald ripening effect. Sodium azide we typically add to the water phase to prevent microbial growth here, so that you do not need to have some kind of sterilization to prevent microbial growth. And in this case, so your first emulsifier, lipophilic, was lecithin, and in the external water phase, for instance, then again, sodium caseinate were used, or wheat protein isolate, or also lecithin. Some different types of emulsifier were used. In this case, you see the compositions. The first step was using a 30-70 ratio, and then this one was actually mixed in equal volumes in the second phase. What do we see about this one here is that actually that if you have a look here for the particle size here of your double emulsion, is that indeed there is a quite pronounced effect of the oil phase that is used. With, for instance, in this case, you see that the droplet size here, if you use the sunflower oil, it's typically about twice the value than if you use the medium chain triglyceride oil. So here we see already a quite significant effect. In this case, actually, that was using the whey protein isolate as a second emulsifier. If you have a look for stability, what happens over time, then basically here there was a small increase over time, but it's quite limited, and anyway that effect was similar for the two oil phases. So here there is not too much of effect. Having a look for the internal water being close to water, then actually also there we see some differences with actually again MCT oil being a little bit better, despite of having smaller droplets. You see that there is still actually somewhat more water included. Surely if you compare that, if you compare different or comparable droplet sizes, then with the MCT oil there was more water entrapped than with the sunflower oil. And actually the most striking result here was that there was especially an effect on what happens during storage, because what you see in this case with this lecithin as a first emulsifier is that actually during storage, if you used MCT oil, actually there was no change, so we have the stable situation. Whereas actually if you use the sunflower oil, then actually you see that gradually the internal water is lost. And actually you also see this here with this microscopy pictures. So that's actually a microscopy picture of your sunflower oil based double emulsion at the start of the experiment, where you see that the oil droplets are fully crowded with water droplets. And actually if you have a look here, for instance, after 1 month, then you see that actually there is only, your oil droplets are only partly filled with water droplets, and actually there is a lot of oil which does not contain water droplets anymore. whereas actually this was not the case with the example. So you see here also that the type of oil actually surely also plays a role. Okay, let's then come to some applications. I said already here, and actually as such you make that component is not present in the external water phase. That's for instance important if you have a functional ingredient but with a very bitter taste or a very bad taste, because if you consume the emulsion, then the taste will be mainly determined by the external water phase. That's what is actually coming in contact with the sensor in the mouth, and maybe even the oil phase, but the internal water droplets, they will survive the mouth, so you will not experience the bitter taste, for instance, of components that are included internally. Another advantage to encapsulate functional foods is also that, for instance, if they do not, if your functional component will be broken down by the acidic pH in the stomach, then actually also here again your component can be protected and you can have a release somewhat further on in the digestion process, because actually the component is not directly released, but actually first your oil droplets have to be broken down before the internal water becomes accessible, so which can also help to improve the effect of your enclosed component. Alright. And so if you have a look for encapsulation, what to do then actually, well, what I have shown here is that, for instance, if you use whey protein isolate, whey proteins, as your component entrapped in your internal water phase, well, what this shows is that surely there you can have a very good encapsulation in your internal water phase, and that also during storage, if you use big hydrophilic molecules like proteins, that actually they will remain nicely included. So here you see actually what happens upon 2 weeks at room temperature, and actually what is shown on the one hand is your water yield, that's actually shown in blue, and the green symbols indicate the encapsulation efficiency of your protein. So you see that actually here we have about 90% of encapsulation efficiency, with actually and with hardly any change during storage. So again, in this case, your proteins, they are so big, they could also only be released if they can go through the oil phase, and actually your proteins are not soluble in the oil phase. So as such, they are really locked in your internal water phase, so there is no release component here. You might wonder, why do we not have 100%? Well, that's of course, remember that during your emulsification, there can be a little bit of destruction of your internal water droplets. So that's like, in this case, your 10% is lost, but that's actually quite a limited amount. And so during storage, there is no further loss. I talked already about osmotic effects, and that's actually another thing that is shown here. It's about dilution. And what is shown in this and the next slide is the effect of so-called hypoosmotic dilution. So it means if you dilute your double emulsion in a liquid that has a lower osmotic strength, which has a lower electrolyte concentration than the concentration in the internal water phase. And because what we know in that case is that if your external water phase is lower in concentration than your internal water phase, then the osmotic pressure will be bigger here. And actually then water will be sucked osmotically, because that's shown in here. If you have a higher osmotic pressure inside than outside, then there will be a tendency for water to be transported from the zone of low osmotic strength to the zones of high osmotic strength, because again, water can go through an oil phase here in this case. And that then of course can have a number of effects. Actually, what you would have in this case is that you can have an increase of your entrapped water on the one hand. Of course, as long as your oil droplets remain intact. What has been described also is that if there is too much of swelling here, that actually also your oil droplets can be broken osmotically, that they can be burst, and then of course it would mean that your entrapped water would be released if there is too much of that kind of effect. So that's the two things that can happen. We had a look, in this case, again using still the whey protein as your entrapped component, and here what we did in this case was indeed do measurements after dilution, after diluting your emulsion with the liquid with a lower osmotic strength. And so what you see indeed is that if you have a look for the water, that actually your water yield is like doubling. So actually the amount of water that is present inside your oil droplets becomes doubled because your water is osmotically transported from the external phase to the internal phase. On the other hand, what you see for the protein, of course there is no protein present externally, so the protein content remains the same, it's only water that is transported. And what you see in this case is indeed that there is actually no bursting in this case, so your protein remains completely entrapped during the same period. It's actually only water that is originally transported here from the external phase to the internal phase by osmotic transport here. Actually during storage, and you see that there is a gradual loss of that additional water. That's because then over a long time, actually also your osmotic agent can then actually slowly migrate through the oil phase, so that actually your osmotic strength will become similar in the internal and external phase. So what this shows here is that you have to be careful with osmotic effects, and this truly shows here that if you dilute and you want to make for particle size analysis and you want to have the fact that your oil droplets do not change, you see that it's important to dilute in an isotonic solution, because if you just dilute in distilled water, then your drops can just become swelling during the dilution step, so that you measure something which is not representative for the original step. I think that this is about the last results. It's actually showing the effect of the properties of your entrapped component. In this last series of experiments, individual amino acids were used as your entrapped component, so not the big protein structures, but much smaller structures. In this case, for instance, here, leucine was used as the entrapped component in your internal water phase. And actually what you see in this case is that individual amino acids, actually they can slowly migrate from the internal phase to the external phase. So in this case, it's actually indicated as the release of your amino acid from the internal phase to the external phase. You see already that there was already, again here, during the preparation, there was some release here. And then actually also during storage, you have actually a gradual release, so that after about 1 month, here in this case, about all of your amino acid actually was released. There is here a number of different curves that's actually considering different concentrations of your entrapped amino acid in the internal phase. But you see that actually the starting concentration doesn't really matter. You have the same percentage, the same degree of release, irrespective of that. So in this case, your amino acids, they can slowly go through your oil phase to the external water phase. And actually to enable to put some number on this, we fitted that kind of release profile with this kind of model, where the important thing is actually your exponential function here. And within the exponential function, there is a time constant, so kind of an average residence time. So that one is actually an indication of how rapidly your components are released. And what you see then, for instance, here is that, well, if you have looked for different concentrations, there is no significant effect in your average retention time here. But if you do this at different temperatures, so these were data at 4 degrees, if you compare 4 degrees refrigeration temperature to body temperature, then actually you see, for instance, that there is typically, or that there is a one pronounced effect that your residence time are typically 5, 6, 7 times bigger. Actually, well, your residence time here is much smaller, so it means that the release here is much faster here. The small residence time means that you have a faster release. So the release is actually much faster, about an order of magnitude faster at 37 degrees than at 4 degrees. So temperature is actually important, because actually temperature determines solubility and determines also your diffusivity. So basically you see here that release is happening by a so-called solution diffusion mechanism. Your component is actually first dissolved from the internal water phase into the oil phase, is then diffusing to the other side, and is there then again then becoming dissolved in the external fluids. Temperature plays a role. That's for instance here again showing that for instance also with Valine, if you show the release at 37 degrees shown in black, Valine at 20 degrees is here shown in black, that was in red, and actually here in blue at 4 degrees. So you see there is a pronounced effect of temperature. But here you also see that for instance the three curves in black are all 20 degrees, but considering different amino acids. With alanine there is hardly any release in 2 weeks. With valine there was actually already quite some release, somewhat less than half. With leucine, more than half. So what you see in this case is that there is a typical difference, or that there is a quite pronounced effect of your amino acid composition. And what we could show in this case is that this is directly linked with the hydrophobicity of your amino acid. So here you have some indication here, the hydrophobicity is here expressed by the free energy for transfer, where you see that leucine is actually the most hydrophobic amino acid. Leucine actually has a quite pronounced apolar part here. In valine, that apolar part becomes smaller, so that's already somewhat less hydrophobic. Alanine is still less hydrophobic, and so you also see it here from this value. And actually, the glycine is then even less, and glutamine is the more hydrophilic one. So you see that actually hydrophilicity of your entrapped components is actually important. And that's for instance typically shown here in this table, where you see that for instance for glutamine, the more hydrophilic amino acid, well then you see that here we have residence times of hundreds to thousands of days. So it means that here it takes 1 year for the component to be released. So that's of course what you want to have no release. So that's okay if you have a very hydrophilic component. But the more hydrophobic ones, so leucine was actually one of the more hydrophobic amino acids. So then actually you have a lot of release in a couple of days. So in that case, that's not very good if you want to have a commercial product which has to be stored for so long. So here you see that actually molecular characteristics play a role. It's especially the hydrophobicity, the solubility in your oil phase that drives that one, with again temperature also very important. There's more information in this slide, but I had already assumed that time was running out. So let me come to some conclusions. What I wanted to show during my presentation is that double emulsions are quite complex structures. The Oswald ripening effect is actually an important one to keep in mind, because that can just lead to loss of your internal aqueous phase in the double emulsion if you do not have an Oswald ripening inhibitor. So that was something that is typical for double emulsions. I've shown that the oil phase composition using a normal triglyceride or a medium chain triglyceride, for instance, also can have quite some effect here. And what I've also shown here is that, for instance, if you do a dilution with a dilution medium that has another osmotic strength, that actually also it can quite affect your double emulsion. So it means that double emulsions are indeed sensitive to environmental conditions with osmotic stress due to having a different osmotic effect at the internal and external water is surely something to keep in mind. That will be also important during oral ingestion and coming in the digestive system, because then surely there will be also, you will not have similar osmotic effects in your digestive system as for the entrapped water, so that also there will play a role then for the final result. I also have shown that, well, especially if you want to characterize the internal water droplets, here that you need some kind of specific characterization techniques. Water droplet size I did not discuss in this case, but that also requires a special NMR technique. The entrapped water I have shown already here. On the other hand, I think that with the examples I have shown, that I could convince you that double emulsions have surely some interesting perspectives. And as we said already, there are two main applications actually to reduce the calorie content of emulsions here, and on the other hand, you can use it for encapsulation purposes. So with this one, actually I want to thank the persons who produced the data, former PhD students, Dean Meeren, Mathieu Balkan, and Ezra Kutjeman, and Yuri, who is actually still finishing her works, but there are also some results here included. I surely want to thank Universitas Gajah Mada for inviting me here to come back to Yogyakarta for about the third time. I guess it's always nice to be back here. And I want to thank you all for being present at this early hour for your attention. Thanks a lot.
Thank you very much, Prof. Paul, for the very comprehensive review of the double emulsion. So